All right, here we are with the second installment of SHM, simple harmonic motion, as it relates to the mass spring system. This video lesson follows the previous one, where kind of established a lot of the concepts relating to springs, Hooke's law, the mass and the spring combined as the mass spring system, how they oscillate, omega, rotational frequency, how that is connected with the mass of the hanging object and the strength of the spring, K. Went over all the relationships there, stepped you through some virtual experiments using my simulators. Also collected some real data with my motion sensor, which is still on the screen here. And mostly this lesson is now about how do we model these functions? How do we model this motion, I should say? What mathematical functions would we use to model a position versus time graph, a velocity versus time graph? Let's just start with those two. Later we'll talk about the acceleration versus time graph. But do recognize, again, that it doesn't really matter whether we're talking about vertical motion up and down. I'm not sure why that's not, oh, I have to play. Whether we're talking about, oh, it's in slow motion. Vertical motion up and down, which you will see on the AP exam, or horizontal motion, more like this one, back and forth. The concepts are all the same. Omega, period, mass, spring constant, modeling that we're going to talk about today, all is exactly the same. Essentially, just take this one and turn it on its head, right? Just rotate this 90 degrees. This becomes the ceiling. This thing now goes up and down and just returns to this. It's all the same. Again, usually for a physics problem that's AP, on the AP exam or in a textbook, again, usually we refer to the middle point, which is right about here, the equilibrium line. Usually we refer to that, we label that position 0, like they've done in this simulator, just because the equilibrium position is, sorry, trying to get it, right there. This is the equilibrium position, right? So it means if I were to, in this case, if I were to take off this mass, then this would just be the relaxed length and the equilibrium line going this way are one and the same. This line would represent the relaxed length and the equilibrium line. Where when you're talking about vertical motion, that's not necessarily the case. Like I've shown here, not necessarily, it's definitely not the case, because the equilibrium position here references the fact that gravity is pulling down and the spring force is pulling up, and those are balanced. So this dotted line right through here would be the equilibrium line, where if I remove this mass, the equilibrium line and the relaxed length are not at the same position. So that's only one difference, I guess. It's one difference that I can see. Other than that, it's all the same concepts. So let's start talking about the modeling. If we were to look at sinusoidal functions, trigonometric functions, which is sine and cosine, not tangent functions. Tangents involve infinities that don't apply here. But the sine and cosine function have no infinities, right? There's no undefined positions. There's the domain is all real numbers from negative infinity to positive infinity. The range for a sine and cosine function is also limited, right, to some positive value and some negative value. And the function produces values that bounce back and forth between some positive number like 4 and some negative number like 4, positive 4, negative 4, positive 4, negative 4. The range would be between those two values. While a tangent function, for example, has ranges that go from negative infinity to positive infinity as they approach the vertical asymptote. So point being, tangent functions play no role here. Sine and cosine functions play a nice role, and you'll see why. If I were to now graph y equals sine x, that is it, right? Wow, that's nice. That is what we saw when I collect physical data, right? This is my real data from my real motion sensor that I have still dangling at my knee right now. And when we, as physics people, look to math to say, what can we use to model this? What kind of functions can we use? Wow, the sine function looks nice. It looks like we should be able to do something with this to make it work for us, right? And notice that when we look at a cosine function, same thing can be said, right? Cos x. Oh, nice, right? Those should be good, two really nice models for us, and they'll have, places and, uses in specific places for specific things, and we can talk about that. Again, no, right? Range goes from plus infinity to negative infinity, and you've got asymptotes that go like straight down, and so boom, no. So let's talk about the sine. Let's start with just a sine function. In fact, let's not start with sine. Let's start with a cosine function. I'll explain why I'm going to start with that one first. The reason is when you go back to something like this and your typical AP problem that relates to this picture and this motion, usually what they do is they imagine, or describe that somebody has taken it from its original length, grabbed this thing with a mass attached to it, stretched it out to some position here, and then this would be 0 seconds, t equals 0, and then they start the experiment, and then they release it. And this thing now goes back and forth between some positive position. I don't know. They don't give us numbers here, right? It just says x equals 0. So maybe this is like 0.1, 0.2, 0.3, 0.4 centimeters. I'm just making that up. But this might be like, I didn't mean to say centimeters. Let's say 0.4 meters, which would be like 40 plus 40 centimeters. This would be minus 40 centimeters. They go back and forth. The point being is that when you begin, again, the whole point of this is to track the motion of this thing. And technically, could you predict exactly where this object is on this number line at any random amount of time? Can you predict exactly what its position is? Can you predict exactly what its speed is? Can you predict exactly what direction it's moving, left or right? Can you predict exactly how much force is in the spring? What its acceleration is? And the answer is yes to all of those questions. How much? And there's the whole conversation of kinetic energy and potential energy, which we haven't even touched on yet. All of this stuff is well understood and modeled by formulas and physics laws, right? And so starting with the position function, position versus time, we usually use, and that's not necessarily a good example of that, because I randomly clicked, this thing was going up, down, and I just randomly went and clicked collect. If I could have, to try to make it fit like with an AP problem or a textbook problem, I would have hit play right when it was this spot right here where I'm wiggling my mouse. Like this was right where the first data point would come in. So this be moved over to right here. And then it would go up and down from that point. And for that reason, and going back to the virtual one here, this would be like plus 0.4 meters, right? So back over to here, this would be like plus 0.4 meters. I mean, I can't change this. This is plus 1. This is Desmos, but this would be like plus 0.4. And that would be a good fit for something that is starting at its maximum positive position. It just goes down from there, right? 0.3, 0.2, 0.1, 0, 0.3, 0.2, 0.10, right? And this point right here is now corresponding to when it's in the middle, 0, then negative 0.1, negative 0.2, negative 0.3. That's these here, negative, right? Negative, fourth quadrant, negative 0.1, negative 0.2, negative 0.3, and so on and so forth. This whole section that I'm looking at with the mouse here, this is all to the left of the equilibrium, these points as it goes this way. And then again, these ones above the above the 0 mark would be all it going from here to here, right? And so we usually use a cosine function as a good model, assuming that you've timed it in such a way so that the initial position is the maximum positive position. Of course, that matters, right? If we decided to make this other position, the fully compressed position, the initial position, and started to say, okay, now start your watch and let's make this 0 seconds and start tracking it from here. Then at 0 seconds, the initial data point would be negative 0.4. And that means this point would have to be down here in the negative 0.4, and then it would have to go up from here in this direction, right? So that initial starting point, called the initial condition, where is that thing when you start tracking it, totally affects whether you pick sine or cosine, or whether you have to shift this thing right or left. But we're not going to get into those complications because we don't really have to. Point being, again, that usually your introductory level problems say assume, as we have here, assume that the initial position corresponds to the maximum position, and we start tracking its motion from here. This would be the 0-second mark, right? This thing goes back and forth. Now, the distance from here to here is, again, how far you've stretched it from where it started. That's the amplitude. If that was 0.4 meters, then the distance from 0 up to here would be 0.4 meters. And therefore, the distance from here down to the lowest point would also be 0.4 meters, because it's going to go from the middle up to 0.4 meters, middle to 0.4 meters, and then it's going to go from the middle to the negative 0.4 meters, from the middle to negative 0.4 meters, and just keep repeating back and forth, right? So this cosine function fits that well. How do you control the height of these, known as the amplitude? Again, referencing the amplitude, a common misconception is that in this function that we're looking at here, that the amplitude is 2, because students say that this is 0, 1, this point is 0, negative 1. So if it's going from 1 and negative 1, then the full amplitude is 2. It's the most common wrong answer. The amplitude is how far it's stretched from equilibrium. It's the distance from the middle to the top, alternatively from the middle to the bottom, right? So the amplitude of this function is 1. How do we change that to model it? Because we wouldn't say that this function only works if you stretch it out by 1 centimeter or 1 inch or 1 foot. No. How do we control that? How do we change this so that maybe I pulled it 0.37 meters? Maybe from here to here was 37 centimeters, and then I release it. How do I make it so this function has a maximum of 0.37? What do I change on this? The coefficient is 1, right? If I change this to 0.37, now the maximum point is 0.37, right? And that would work for an experiment where you originally stretched it by 37 centimeters and then let go, right? Or no, he started by stretching at 1.2 meters. All right, well, then just make this 1.2, right? Now the maximum value is 1.2 and the minimum will be negative 1.2. Right? So this coefficient, known as the amplitude, is a full control on that full swing from one side to the other side. Or really, it's more specifically a control, a numerical value that you use to control the displacement from equilibrium, which is called the amplitude. So with that said, we usually reference the position as x, which you're familiar with, usually in meters. I'm not sure why it's so thick. Let's make it a little thinner. And then we usually write x as a function of t. Now, why? We could write that for all our kinematic, well, 2 of our kinematic equations, right? Sometimes we write v final equals v initial plus at. Other people like to write, well, v is a function of time, and that means the same thing, right? Doesn't mean v times t, it means v is a function of t. Just like some teachers write y equals 5x, and then another teacher writes y as a function of x equals 5x. It's just reminding you what the independent variable is x. Y depends on that, right? The independent variable is t in physics most of the time, right? So even though we don't usually write this v of t, for whatever reason, people who write textbooks and stuff, they typically, when they get to this section, they write x of t. They could just write x, meaning x is some position it has at some given time t, right? So we know that a now represents amplitude, is what we were just talking about. It's a coefficient, it's a number. It's the maximum displacement, which is created when you put this thing into motion. If you grab it and pull it 5 centimeters and let go, it'll go 5 centimeters, negative 5 centimeters, 5 centimeters, negative 5 centimeters. It's set by the original distance you pull it, and this would be just 5. And usually we use this as just a positive number. Think of it as an absolute value. Yeah, the value goes from -4 to +4 and -4 to +4 if you pulled it by, I don't know, 4 meters. But the a value doesn't control the plus and the minus. The cosine function does, right? The cosine function has that ability to range. Let's return this to a coefficient of 1. It has the ability to range the cosine function from a value of +1 to -1 to +1 to -1. Why is that? Well, that has to do with the unit circle, right? This all has to do with the unit circle. If we start, let's say at a little bit of an angle here, right? We see there's a triangle in here. This is some little tiny angle, and I drew that bigger. This is the angle, this is adjacent, and this is the hypotenuse, right? So if you were to drop this down and lay it right on top of this, remember that cosine of any angle is adjacent over hypotenuse, right? If this is like a stick here and you just drop it down on the floor, then the length of the stick and the length of this piece they're lay on top of each other. They're one and the same. So in this position that I'm showing, this one would be a little bit longer than this one. But when you drop it down to 0 degrees, they're the same length. And whatever this is divided, it's 1, right? Cosine, that's why cosine of 0 degrees is 1, right? If we were to swing that to the opposite side over to here and think of the same concept, this value, if I don't know, whatever it was, let's just put a number in there. If this was the number, 4, then when the hypotenuse is dropped down to the lowest position, the hypotenuse becomes 4 and the other adjacent is 4. 4 over 4 is 1. On the other hand, when you're in the second quadrant over here, this would actually be -4. And then when you drop this piece down to lay over the top of this one, hypotenuse, as you know, is always 4 because of Pythagoras theorem. Then you'd end up with the ratio of adjacent over hypotenuse, 4 divided by -4 divided by 4. Well, that's -1, right? And this is an angle of 90 degrees. That tells us cosine of 90 is -1. And that's why the cosines ranges as long as the coefficient is 1, which we did here. The range is +1 to -1, +1 to -1, right? Because eventually it's going to rotate back around and we'll be back to this same thing here. And back to this one and back to this second one. It would just go from +1 to -1, right? So cosine function and sine function both have that feature. We'll talk about the sine one in a minute, but we're on the looking at the cosine one. It has a control. It's a decimal. It ranges from 1 to -1 and every number in between, right? You can just pick randomly anything. I don't know, cosine of 32 degrees. Cosine of 32 degrees. Let me pull out my calculator. Will it be a number above +1 or below -1? No, right? Here we go, cosine of 32, enter. I got 0.84, right? Because it's in between +1 and -1, right? Any angle in between 0 and 90 degrees, and surely even when you go like from here to here, even though that might be like 170 degrees, the reference angle in here that we're drawing in this little triangle is actually 10 degrees. If this was 170 degrees, then this little reference angle in there would be 10 degrees. And well, all reference angles are between 0 and 90 degrees. That's the point of a reference angle. So the function always varies between +1 and -1. So it gives us that ability to control the output of x of t. Right? Because if a is always just a number, like a constant number like 4, because you stretched it out by 4 meters, yeah, that's far, but let's just say it was 4, then this value, this cosine function will be, at times it'll be 1, right? We just talked about that, 0 degrees. Then cosine of 0 is 1, and 1 times 4 would just be 4. And there's other times where theta comes out as -1, or I should say there's other angles, pi radians or 180 degrees, where cosine of that becomes -1. And you'd end up with this whole function here comes out as -1 times a, and well, you get -a, right? So the cosine has that feature of not only diminishing or increasing its position at some given time, right? Because this is a large position if you want to think of it that way. And then as we go forward and the position's decreasing. The physical distance from here to here is getting less. And the cosine function has that really great feature. It doesn't only change the physical output of the function as it goes down like this, it also has the ability of dipping into the negative and being above in the plus at times, which we know happens, right? So this is the general way we would model the position function, x of t. However, we don't write theta. We have, because this is in terms of time, right? This involves time. Where you'd say, where's time? There's no time there. It's theta. Math class, that's all good, right? 5 cos of theta, whatever. Cos x is usually what they put. But if we look here, right, in the real world, like this is time. This is the time axis that we're looking at, right? So how do we incorporate and fold time into this, right? Because it says x is a function of time. Well, let's think of omega, right? Omega probably is going to come in here because omega is in units of radians per second. We know t is in units of seconds. So technically, if we multiply omega times t, we'd end up with radians over seconds times t, which is seconds, and we end up with radians, which is an angle, right? And we know theta is an angle, right? This is an angle, and it could be in degrees, it could be in radians. But we're talking radians here. This whole modeling, by the way, involves radians, not degrees. Yeah, projectile motion, trigonometry stuff, when we do right angles and vectors, it's all degrees. But you need to know once we get into rotation, which we're in the rotation unit, we're talking radians as it rotates. Okay, and when we're talking theta in this application, we're talking radians. So that means omega times t is equivalent to radians. So that means we can take this away and put omega times t here, right? Because now omega is just a constant. Omega it's like a wheel that's rotating, but it's rotating at a constant rotational speed. The car is driving at a constant speed, v, and the wheel just keeps rotating at the same rate, omega. It's just a constant. Note that when this thing is going up and down, we talk about the angular frequency in radians per second. It's a constant value. If it takes, 1 second if we go back to my image or my simulator, if it takes some amount of time, I don't know, it takes some amount of time to go from the middle to the bottom, which how many radians would that be? Remember, from the top all the way back to the top is 2 pi radians, which means from the top to the bottom would be pi radians, which means from the top to the middle is pi over 2 radians, right? So it's broken into quarters. This is the first quarter. This is the second quarter. This is the third quarter. This is the fourth quarter. 4 over 4 is 1 full cycle. So it takes, let's just say, 1 second to go from here to here through a radians of pi over 2. Then, of course, it would take 1 second to go from here to the bottom, right? To go through another pi over 2, 90 degrees. And it would take another second for it to go through another pi over 2 back to here, and another second to go from here over here. So if it takes the same amount of time to go through each chunk that I'm showing, and omega is that. Omega is referencing how long it takes to go through some amount of radians, then omega must be constant, right? Omega is a constant number. And in fact, we already talked about omega, right? We already talked about omega in the first lesson. Omega is a function of which two properties? Which two properties of the mass spring system directly affect omega? These two, right? We already proved that omega was the square root of k over m, which means we could technically stick that right there to really model this thing with a beautiful feature, with all of the beautiful features you would want, right? You're taking a generic math tool like cos x and build your own sundae, right? You start off with the basic features, a bowl and a clump of ice cream, and then you can put on whatever you want to make it look like whatever you want. That's what we're doing. We're borrowing this basic tool and now building it to fit our needs. We have A as a beautiful feature, the coefficient that can control, again, the distance from the left or to the right of equilibrium, or for the vertical one, the distance above or below equilibrium. And now we have this other great tool, omega, which fits in right here. Yeah? Right? So that means we can write x of t equals a cosine, square root of k over m times t. So as a function, this is a constant. It's the distance you originally pulled it before you let go of it, right? It's the amplitude. Mass is constant. It's called the spring constant. It's constant, right? These are all numbers, right? So in a real scenario where, like, okay, Mr. Kurtzak pulls the block 5 centimeters and to the right, and then lets go of it. What formula will model its motion as it goes back and forth? We pulled it 5 centimeters, and point A is 5.05. We'd have to know the properties of the system, K and M, right? Maybe in the problem they tell you that K is 20 newtons per meter, and the mass is, let's make it nice, 4. Okay, so when we get here, we would do square root of 20, and for K, over 4. That's not nice. Make it 5. That's nice. So let's say the mass is 5. Well, 20 over 5 is 4. Square root of 4 is 2. So that means the formula that we'd use to model this would be like this. We actually would put those numbers in dependent upon what the system properties were, K and M, which are all input here, and amplitude, which is input here based on how far I stretched it. And if I were to graph 0.05 cosine 2t, 0.05 cosine, and now I'm going to take away what's implied to be here when we say cos x. We're implying there to be a 1 here, right? So if I were to now take away that coefficient and put 2, I was just talking about, if this all came out as 2, I don't know what happened to my settings. It's terrible. Did I zoom in? I don't know what happened. Kind of see it there. I wish I could change the, well, that's fine. So the point is, this coefficient now affects how rapidly this thing goes through its cycle, right? For this particular one, let's see. This would be the beginning when I let go of it. Follow it down. Now it's in the middle. Now it's at the bottom. Now it's returning back to the middle. Boom, right there. So what is the period? 2.3 would represent the physical position, although that's not right. Something's not right here. I don't think I saw that right. Try again. 2.3. Why is it saying 2.3? Yeah, that's not right. So 3 pi over 4, this is like x comma y, right? So the time value is 3 pi over 4. So I don't even know what that is, 3 pi over 4. Pi is like 3. 3 pi is like 3 times 3, like 9. 9 over 4, 2 and a quarter. So that means this is, yeah, but which makes sense, right? This is 2. This is 2 seconds here. So this is like the 2 and a quarter second mark. So that means the full period is 2 and a quarter seconds. Right? And if I were to come back to here, remember we have this. If omega, as we just worked it out, I just remember omega was right here, square root of 20 over 5, which came out as 2. Then I have 2 pi over 2. So why is that not coming up? Did I enter something in wrong? I might have. Should just be pi. It should be 3.14 seconds. So I'm not 100% sure what's going on there. Let's see, 2x. I'm not 100% sure. So I'm not really sure on what's going on. These are weird to me. Yeah, it switches to like, yeah, I don't know. I don't know what's going on there. Anyways, this is still all correct. What I'm saying is the 2 value, the omega, is our way of controlling how rapidly it goes through the cycles. And if I were to change that, let's go over to back to Desmos or back here. If I were to put the number, let's say 10 instead of 2, what will happen to the shape of this? Will it change the amplitude? Will it change how high and low it goes? If I change this number 2? Well, no, because that high number and low number is only affected by this coefficient, 0.05, right? So it has to be a 0.05 and negative 0.05. But if I put the number 10 in here instead of 2, let's see what happens, or number 20, let's say. Oh, see that? This is now a high frequency oscillation. See how it's zoom, 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 going through its oscillations very rapidly. Now we've got a period of, this is weird, pi over, yeah, I don't even know, pi, why is it doing it? Because this is like in this radian mode thing, I think. But I can see right here, what is this, 1.5, so this is like 0.25, oh, there we go, that's showing normal numbers, 0.25 seconds. So now, as we go from here back to here, yeah, that's weird again, maybe that's still pi over 10, about 0.3. So it's about 0.3 seconds, right? So the point is, this is a small period. This that you're looking at would be a good model for this. Zoom, 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 zoom. Zoom, 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 zoom. Small period, right? Omega is very high. Again, if this number was much smaller, not 20, but like the number 3, boy, that's going through its cycles very slowly. Now it's got a period of from here all the way to here, all the way to here, right? So from the top back to the top, it's like a little over 2 seconds, right? So it's a much longer period. That would be a good model for this one. Ooh, very slowly going through. Right? Long period, right? So this omega, this coefficient to the t, is a beautiful control for how rapidly it goes through its cycles. And it's fully controlled by K and M. So we end up with what I have written here. The general format for modeling oscillatory motion for the mass spring system, which, let me, by the way, point out, you might think, who cares about springs? Like, where does this really, where does this get applied in the real world? Anything that goes back and forth. So even for rockets, when they're, taking off, they shake, they get vibrations, and vibrations can be really bad because vibrations can actually increase in amplitude due to something called resonance, which I haven't talked about. Which means the vibration gets more and more violent. The amplitude actually increases with time to the point where parts start failing. They start falling apart. So when they model the vibrations of a rocket, for example, due to the fact that the engine's burning, they use this. They even use this to model vibrations of atoms. Atoms actually vibrate in and out. So they use this. A would be how far the atom stretches and then compresses and then stretches, and they physically vibrate like a spring. The springs actually are beautiful models for atomic motion. This could be used to model the brightening and dimming of a star. They have pulsars. Pulsars, for example, are these stars that get brighter and dimmer, and they keep periodically in the same amount of time. After 2 days, it's really bright. 2 days later, it's really dim. 2 days later, it's really bright. 2 days, it's a little dim. And this brightness of the star varies, called the pulsar, pulsing with its brightness, diminishing and increasing. Which functions do they use to model that? This. A would be the maximum brightness or yeah, A would be the maximum brightness, and this piece right here would control how long it takes for it to go through its full cycle. Those are just a few examples. Like these are this model is used millions of different cases in science. So it's important for me to point that out as your teacher that, again, you think, who cares? Like this can't possibly be used. Like where would anybody do this? Who cares about this? But that's the point of physics. The point of physics is that you can do very simple experiments and learn things about certain systems and then realize that you can apply these same rules to all sorts of things, even buildings that sway, like tall buildings that sway back and forth because they're the wind is blowing and then diminishing in its gusts, and then blowing, and sometimes you get this effect of the wind blowing and then not blowing, blowing and not blowing. Which, by the way, you could look up the Tacoma narrow bridge. I mean, I'm not going to show you this whole video, but like this whole bridge from the effect that I'm talking about. Oh, God, it's super loud in my ears. Sorry. This whole bridge, literally from the wind, starts doing this, creates a standing wave. This is real. This is real. And this bridge eventually came down. Eventually, they went on for hours. They all eventually, everybody was safe, and you could see this thing. What formulas would they use to model the motion of this thing? The formula that I have on this. And they place certain, nowadays this can't happen because they place certain support structures in certain positions based on this formula to prevent that from happening. Similarly, like with the bridge, with the buildings that go back and forth, they literally put giant masses on the bottom of bridges. I'm sorry, on the bottom of buildings in the basement, so that as the tip of the bridge goes to the right, on the bottom of the building, there's this giant heavy mass that literally moves to the left to bring the top of the tower back. And then as the tower swings to the left, it would sense that and move this giant heavy weight to the right. And it goes through periods back and forth, right? A would represent the full displacement from the vertical line that the tip of the building goes from left to right. And this control feature is how rapidly it's going back and forth. They can damp that motion with big weights in the bottom of the building that counteract the motion on the top. So it's worth me, pointing that out. Very, very important that you recognize. It's very useful in many, many different applications in science. Anything essentially that's periodic, anything that repeats itself over and over again in a symmetric way. These are useful. So this is our position formula. All right. So now what we're going to do is look at, again, back here, the idea that when I took this data down, we're going to have to start talking about velocity versus time, that when the position is a maximum, like if it was the up and down, let's just say mass going up and down, then at the top, when it's fully compressing that spring near the ceiling, it stops, right? And when you trace this down again, you see that the velocity is zero, right? Or when it's at the bottom, when it stops at the lowest point, the velocity is zero. So we need a new function for a velocity versus time graph where these two functions are called out of phase. They're out of phase by pi over 2 radians or 90 degrees. What that means is when two sinusoidal or cosine and sine are both considered sinusoidal functions, when they're out of phase, it just means that they're not perfectly in alignment. Like this is the tip of this one, the crest right here, and you can see this one's a little bit to the right. So that means the difference between, if I drew a vertical line straight up, brings it here. The difference between here and here is actually pi over 2 radians. Meaning if I took this one and dragged it pi over 2 radians to the left, it would be a perfect match for this one. I mean, the amplitudes aren't the same, which you can see. But the maximum of this one would correspond with the maximum of the other one. When two functions like this are out of phase, it means that when one of them is a maximum, the other is zero. And when one is a minimum, this one is zero. Right? This one is minimum, this is zero, and this one's maximum, this one's zero. They're out of phase. Sine and cosine functions are out of phase by pi over 2 radians. It's a beautiful, it's like set, it's like meant to be, right? If we go over to Desmos and take a look at what I'm talking about, let's just put a cosine function in, which we already used for the position graph. Wish we could do two of these, but like I said, if one of them is a max and the other one's a minimum, when the other one's a maximum, then they're out of phase by pi over 2. So if we look at the cosine function, which is a maximum right here, and I change this to a sine function, it's 0. See? When cosine was a maximum, this one is 0, right? Or when this one right here is a maximum, which is one block to the left of the 2, let's see what the sine function, the cosine function is. One block to the left of the 2, it's 0. See? They're out of phase so nicely, perfectly set up for modeling position and velocity, right? So if this cosine function is the model for position, which it was, as I've said, assuming that you stretched it out and started timing at the moment you release it when it's at its maximum position, then the sine function will be a perfect match for velocity, because when you start by pulling this thing all the way to the right and then releasing it, again, it's not moving. We're assuming that someone just grabs it and then holds it here with their hand, and then they release it from here. This is 0 seconds. This initial speed is 0. Velocity is 0. It's not even moving, right? So that means this sine function would be a good match for that. And then if it's moving, if we have a function that now goes like this, which is in the positive direction, this would actually be indicating that it's, if this is our, again, our velocity graph, that's indicating the velocity, this would indicate positive velocities, which means it's moving to the right. But that's not a good match because this thing's moving to the left. We need a function that's going to, once released, yes, give us a 0 at velocity at release, but moments after release, it has to give us negative velocities because it's heading to the left. So yes, no, these have to be negative. So what can I do to this? What can I do to this graph so that this point, let's say right here, which is at the right corner of this block, you see it's in the right corner, I need it right here. And this one, I need this one like right here. What do I do to this function to make that work? I just put a negative sign in, right? Multiplying all of these outputs originally by -1 will just flip everything for me. So that means the negative sign function works so beautifully. Yeah, right? Because now after release, it's going to be moving to the left with a negative velocity. Negative, 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 negative. It'll have a 0 velocity. This point right here is indicating it's got 0 velocity. Sorry, I was saying that wrong. This part right here is saying that it has a maximum negative velocity. So it's really moving fast in the negative direction. This is a velocity versus time graph. So this is a large negative number indicating it's just moving to the left, negative, with a large speed. Where would that correspond to? Right as it passes through the middle. Boom, right here. It's now still moving left with a large negative speed. That's this one. Now it's still moving left because these are all still negative velocities. Again, it's a velocity versus time graph we're talking about. These are all negative, but the speed is diminishing. The speed is getting closer and closer to 0. Because here is 0 speed. So it's negative is just telling us it's still going leftward, but slowing, 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 slowing. That's these ones. Slowing, 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 slowing. And it stops, 0 speed. Where would we be there? Boom, right here. And now it's going to head with a positive velocity, speeding up faster and faster and faster and faster. Heading to the right, faster and faster and faster and faster. Again, maximum speed right there, which would be right here. Maximum speed, heading to the right, positive velocities. So this is a beautiful thing. That means when you use the cosine function to model the standard problem that I've talked about, which is something starting on the right and then being released, when you use cosine function to model that, which is the appropriate choice, then the appropriate choice for the velocity modeling is a negative sine function. Negative sine function. So let's jot that down. What would the A be? You have to also think, what would A be if we're talking velocity versus time? Well, A affects whatever these maximum and minimum values are, right? So if this was representing velocity, which it is, a velocity versus time graph, then this point is its greatest speed, negative because it's heading to the left as it moves through equilibrium. This would also be its greatest speed, positive velocity because it's heading to the right, passing through equilibrium. So these maximums and mins, which we know are controlled by A, are now representing the maximum speed. See? So now what we're going to do is erase these, erase all this, and we usually write the function that models the velocity as it goes back and forth as v of t is usually how we write that. We put a negative in the front, which I kind of forgot about, so let me make that a negative a. And so just so it's clear, I mean, you can think of writing it as a, and then you can think of a function here, which is the negative sign function I talked about, right? So we just talked about negative sign function. So nice, right? However, usually we would factor that out, right? We would just pull that out as negative a. And A, we don't usually call it amplitude anymore. A is usually only used as a symbol to represent the maximum displacement from equilibrium for the position versus time graph. A gets a new name, which is usually written as V max. So it is the coefficient. It's still a coefficient to the sine function, but it controls the no, actually, I'm taking that back. Sorry. So there's some other thing that I haven't proved yet. So the negative still stays here for now. Let's leave it that way. Negative a, and it turns out that omega is actually goes in here. So the coefficient. This is the coefficient now for our new velocity versus time graph. A still does represent the amplitude of the displacement. The position amplitude. So, and omega that's our square root of k over m, right? I don't have to stick it in right now as square root of k over m. Just in the back of your mind, omega is a square root of k over m. All right. I'm going to erase that because I don't want to get too confusing. And then this part is the same as it was before, just omega times t. Just as we had on the position versus time graph. Again, these two omegas that you see in here can be re-expressed as square root of k over m, and that could go in here and that could go in here. So the negative is there because of what we talked about, where it starts out moving leftward in the negative direction. Negative is there, check. A is still our normal position amplitude. If I pulled it out by 5 centimeters, then this would be 0.05. Even for the velocity versus, again, the velocity versus time model. Negative. So this is still the position amplitude, and this is still omega, the same old omega. And this is still omega t, just like we had before, which could be k over m, square root of k over m. So it turns out that the maximum speed, which is what I was about to do before, A times omega, A, position amplitude, times omega is actually V max. So this quantity represents the maximum speed. We usually think of that as max speed. The negative is already there. Excuse me. The negative is already there to deal with the fact that the velocity is going to be plus when heading to the right and negative when heading to the left. That is already there because remember, sine also goes through pluses and minuses. Still goes through plus and minus cycles and plus cycles, right? So there's times where the sine function is going through its minus cycle, which is down here, and then you end up with a minus and another minus, telling us that the velocity that it comes out of this function would be a positive. Omega is always positive. It's a square root. Otherwise, yeah, it can't be right. And mass can't be negative, and neither can K. But the point is, this V of T graph will still go through its own pluses and its own minuses as we would need, its own minuses and its own pluses, because the negative there stays, but the sine function varies. It's on its own through its own plus cycle and its own minus cycle. Its own minus cycle and its own plus cycle. So there's times where the sine function is minus, and this minus gives us a positive velocity. And there's times where the sine function is plus, like up here, where this plus and this minus reports a negative velocity. And we need that because we know that our thing's going to go left and right. The velocity is going to be plus when heading to the right, negative when going to the left. So it works, right? So know that this is the formula that models V versus T. Negative A omega sine omega T. Know that the coefficient is really A times omega, and that is the maximum speed. So let's go to another page. X of T is A cos omega T. Check. Our velocity versus time graph is negative A times omega. In fact, let's just write it like this. V max, actually just write it like this. Write a negative first. Negative V max times sine omega T. However, I haven't proven this to you, but experiments can be done to prove that it's true, that the maximum speed it has as it passes through the middle, as it passes after you've released it, and it's passing through the middle, the maximum speed in meters per second happens to be equal to A times omega. And know that in all places, you can express omega as square root of K over M. Another important thing, in fact, before I go into that important thing, we can talk about energy right now, right? As this thing, when it's fully stretched out, all of the energy is potential energy, spring potential energy, US, right? In this position, if you're holding it, about to release it, which is 1/2 K delta X squared, where delta X is the distance between here and here, the distance you've stretched it, right? And then as you release it, that potential energy decreases. The kinetic, which you can probably see, I guess, on their thing here, this potential energy is going to be decreasing, this number 322, as I keep going. Where is that energy turning? What is it turning into? It's transforming into kinetic energy, right? So as this thing moves to the left, the kinetic energy is going to be increasing, which we know because the maximum speed is in the middle, boom, right? This green one is going to get larger and larger. What's going to happen to the total? Well, if there's no loss of energy through friction, which could be under here, but if there's none, if they tell you there's a frictionless system and there's no air resistance, then the total of these two numbers never change. You could add these two up, 690.7 plus 559.28, whatever, on a calculator, hit enter. And then at any other random time, add these two numbers up and it's going to come out as the same total. So the total mechanical energy is not changing as this thing goes from its starting position, which let's say is here. Although the potential energy is decreasing, it's just transforming into kinetic energy. The total stays the same, right? And at the middle point, it has no potential energy because this is the distance, this is the length of the spring when there's no block here. It's its regular length. So it has no, and remember, there's F equals K delta X, right? So there's no force in this because there's not stretched beyond its normal length at the middle position. So that means all of the initial potential energy that it starts with is fully transformed into kinetic energy here. So the mechanical energy is fully kinetic in this position, while the while the total mechanical energy is fully potential energy here. The total mechanical energy in the middle is some combination of both, potential plus kinetic. In the middle, the total mechanical energy is just kinetic, zero potential. And then as we go past that point, the kinetic energy starts to decrease. It starts losing some speed because it's compressing the spring, and the spring is pushing to the right as this thing moves left. So it's losing kinetic energy. That kinetic energy is just transforming back into potential energy as it compresses, because the compressed spring holds potential energy just as well as a stretched spring. And in this position, all of the total mechanical energy is all potential again. and then it just repeats, right? Now it starts turning back into kinetic energy. Yeah. So even from a theoretical point of view, we can say that the total spring potential energy at a position of plus A, which again is when it's at its all the way over here, the total potential energy at this position, remember this is referred to as A, the amplitude, has to be equal to the kinetic energy when x is equal to 0, which is in the middle, which is here, right? So all the potential energy becomes kinetic energy. So let's just see what we get. We get 1/2 k delta x squared, where delta x is the distance, again, from 0, from 0 to wherever it is. So if it was like this, delta x would be the distance from here to here, but negative. If it's over here, delta x is the distance from 0 to the plus, from the distance between here, which would be plus, positive delta x. Delta x just represents the displacement from equilibrium. But if I'm going to reference this position here, the displacement is A. That is the amplitude. At this full extension position, the displacement from equilibrium is the amplitude, right? So I can just call that A. And that all of that becomes kinetic energy, 1/2 mv squared, right? So let's see what happens. 1/2 Ka squared equals 1/2 mv squared. What I'm doing is modeling the exchange of energy and transformation of energy from potential at the fully stretched position into fully kinetic energy in the middle. 1/2 Ka squared equals 1/2 mv squared. That's in itself a lesson. That's how you would model that. Someone said, what is the total mechanical energy of the system? 1/2 Ka squared. It's whatever it starts with. It's the addition of these two, but that's not actually worth looking at. Whatever this 1/2 K delta X squared is, if it came out in this position when you're holding it as 1,000 joules and someone says, what is the total mechanical energy? It's whatever 1/2 K times delta X squared is, where delta X is A, the amplitude. If it comes out as 1,000, then the total mechanical energy is 1,000 joules. How about now? Well, it's 1,000 joules. How about now? It's 1,000 joules. At all points, the total mechanical energy would be 1,000 joules if 1/2 Ka squared came out as 1,000 joules, because we're assuming no loss of energy. If there is a loss of energy, then that's called damping. We'll talk about that later. So this is how we model specifically the idea that the potential energy at full extension becomes full kinetic energy in the equilibrium middle position. The 1/2s would cancel away if I divided both sides by half or multiplied both sides by 2. What else do I get here? I get Ka squared equals mv squared. This v would have to represent the maximum speed because we're referring to the middle, right? We're talking about after it has been released from its initial position. We already said that the maximum speed is right here in the middle. Boom, right there. And that's the point that I'm referencing. 1/2 mv squared is referencing this middle position. That's what this is right here. The full potential energy at the beginning on all the way to the right is equal to the all kinetic energy that it has in the middle. And that's not just any V, that's the maximum speed. So let's solve for V max and see what we get. Divide both sides by M. Now square root both sides, because there's a square here, right? Oops, sorry, move that up a little bit. Square root this side. Well, that gives me V max is equal to, well, this, since these are all underneath at the one square root, I can actually see that as square root of K over M times the square root of A squared, right? Ooh, square root of K over M, that's omega, right? This is omega. And the square root of A squared is A. So that means theoretically the maximum speed in the beginning, the maximum speed in the middle when it passes through equilibrium is the product of A and omega, usually written in this order, though it wouldn't matter, of course. So theoretically, the maximum speed is A times omega. And I've just proven to you what I had written on this page back here. Remember, I just said V max is equal to A omega, right? All right. So that is the formula. Again, all the features are there to model V of t. Lastly, we're going to move on to A of t. Let's just think about it. And then we'll be, we're getting to be done with this lesson soon. But let's just think about it first. If we're looking at A, the acceleration, which is how rapidly it speeds up, rate of acceleration. If we think about Newton's law, right? We know A is F net over M. We know A is proportional to F net. If we're looking on this thing that goes back and forth, remember, as it slides back and forth, let's just say it's like this, the normal force and the gravity force are always going to cancel, just like it would be if it was just sitting there on the table by itself and no spring. The fact that it's moving left and right has no effect on Fn or mg. The vertical forces are always in equilibrium, right? So the only forces that were really sideways forces that we're referring to, in this case, if it was pulling it to the left, would be the spring force. That would be like, these spots here. So if it was moving to the left, right? The force from the force from this, I take that back. Sorry, I just realized I said that backwards. Because as this compresses, it's actually, the spring is pushing it to the right. So sorry. So as it's compressing, the spring force is to the right. On the other hand, when it's, way stretched out over here, the spring force is to the left, right? So the spring, I didn't realize you couldn't see what I was drawing. So when it's fully compressing, the spring is trying to push it to the right, saying, I don't like being compressed, pushing back. When it's stretched out, the spring is trying to yank itself back to its original length, right? So the direction of the force varies from a positive to a minus. If the force varies from a positive to a minus, then the acceleration must also vary from a positive to a minus, because m is just a scalar, just a positive number. These are two vectors. They mirror each other, not in numerical value, but in direction. So if the net force is plus, the acceleration is plus. If the net force is negative, the acceleration is negative. And that net force is just the spring force. Again, because the normal force, as I'm drawing here, and the gravity force would always be canceling, regardless of where Fg and, getting messy there, but Fg and Fn would always cancel. So the force, again, the net force varies, and therefore the acceleration must vary, right? Not only that, the net force is k delta x, right? That is Hooke's law. The spring force is modeled by k delta x. That's Fs. The spring force varies as delta x varies. Remembering delta x can be plus or minus. If we're over here, delta x is minus the distance from here to here. That means the force should be plus, heading to the right. On the other hand, if delta x is plus, which is over here, then the spring force should be pulling it to the left, which is why it slows down, because it's moving rightward, right? In fact, that's why it's actually negative k delta x, because whatever the direction of delta x is, if delta x is plus, then the spring force will be minus because of this. So we have this connection now between spring force and acceleration. And so we're going to point out that there are moments where this thing has maximum accelerations, which would be surprisingly on the end. When the force from the spring is maximum, which it is here, then the acceleration must be maximum. It's going to, moments later, in these few first frames, it's gaining speed at a very fast rate, very high rate. Interestingly, when it passes through equilibrium and the spring has no tension in it, just its regular length, delta x is 0, right? If delta x is 0, then the spring force is 0. If the spring force is the net force, which is what we said, and the net force is 0, then the acceleration is 0. So there's actually no acceleration in the middle when it actually is moving at its greatest speed. And at its greatest speed in the middle, all the kinetic energy is maximum. all the mechanical energy rather is maximum. I'm sorry, all the mechanical energy is kinetic at this point. There's actually no spring force in that fastest moving position. No spring force and no acceleration. And then as it goes past this position, it's now slowing down, slowing, but the acceleration itself is increasing because the force is increasing. So it has a maximum acceleration again here. Acceleration is going to be plus. The acceleration vector will be straight to the right in the direction of the net force, which is to the right from the spring. And again, on the opposite side, the acceleration is also a maximum here, but its acceleration is to the left. Right? So these are the two endpoints. The acceleration would be in this direction. The spring force would be in this direction. Over here, the acceleration would be in this direction. The spring force would be in this direction. Remembering that the spring force and the net force are the same, as long as there's no friction. And 99% of their problems, there's no friction mentioned. But as it moves closer to the center, where there's no net force, because the spring force is none, because it's not pulled, extended, or compressed, Fs is equal to 0, which tells us that the acceleration must be 0. So these are maximum accelerations on the endpoint with 0 acceleration in the middle. So that means we need a function that gives us maximums for acceleration when the position is also maximum. Well, why don't we just use the same function that we had before? We go back to, where's my Desmos? If we started with our position function as this, which we did, for the negative. If this was our position function, we know that when it's at its beginning point right here, this is again when it's here, this is a maximum force and maximum acceleration. Then we need an acceleration versus time graph, that's what we're talking about now, that also has a maximum when the position is maximum. And when this block is all the way on the other side, at its minimum position, this is where the spring force again is also maximum and acceleration is also maximum, in magnitude at least. Right? So we need an acceleration versus time graph that gives us a minimum when the position is also minimum. So we might as well use the same function, right? Because they match each other. So with that said, if we were to, let's just Google this. I'm just curious to see what it will look like as mass spring system graph. I figured I'd find a nice little table or chart because I can write them all out, I guess. And not quite what I was hoping to find. Okay, that's fine. So let me return to here. So now what we're going to do is talk about our acceleration versus time graph. We know it has to have some maximum. In fact, let's not call it A, sorry. It has to have some maximum value, so I'm going to call it A max. It has to go through positive and negatives because acceleration direction changes since the net force changes on both sides of equilibrium. We know it has to have a match for when the position, remember that the position was modeled by a cosine omega t, then this also has to be a cosine omega t. Because if they're both cosines, then they'll both have maximums at the same time. And again, when the position is maximum, the acceleration is maximum, or you can still think of this as maximum in terms of its magnitude. Or if you'd like to better think of it over here, when the position is maximum, again, spring force is maximum, the acceleration is maximum because of Newton's second law. large net force, large acceleration. So these both have to be a match, right? And omega, yeah, that never changes. Omega is always square root of k over m. The only thing we have to think about is what is this? Well, let's see if we can work out what it was, like I did previously with you, where I worked out V max is equal to A omega, right? So we know that the spring force is equal to K delta X, right? In general, delta X can be any distance from equilibrium, plus or minus as well. However, if we're talking about the endpoints, because A max is one of the endpoints, then that's delta X is A at the endpoints, right? So I can technically say that the maximum spring force, Fs max, is K times A, capital A. And technically, I also know that F net equals M A, right? So technically, and this would be, I'm sorry, write it underneath. If I wrote F net max is equal to M times the maximum acceleration. So whenever the net force is maximum, when Fs is max, right? The spring force is maximum. When the spring force is maximum, the net force is maximum because that is the net force. The up and down forces from normal force and gravity cancel. So the spring force to the left is the net force, right? So we have F net max, recognizing that F net and the F spring force are the same at all times. So that means when F net is maximum, we can just write that as Fs max. So it has to be that Fs max is equal to both of these. So that means I should be able to set them equal to each other, right? So I'd end up with K, one moment. Get out of here. So I can set these equal to each other. I end up with Ka is equal to Ma max, right? And because they're both representing the spring force, the maximum spring force. One's using Newton's second law, the bottom one. The one above it was just using Hooke's law. So we're combining Hooke's law with Newton's second law. What do we get? A max is equal to K over M by dividing both sides by M here, right? Times A. Now, K over M, we recognize from omega, right? We knew omega was square root of K over M, just in terms of K over M is recognized from that. So that means omega squared is just K over M, right? If I square both sides of that, I get omega squared, and the square root of the square would undo each other. So K over M is the same as omega squared. So I'm looking more closely at this right now. This result that comes from setting those two things equal. A max equals K over M times A. So I ended up with A max equals K over M times A, right? But K over M is equal to omega squared. So that means the maximum acceleration should be equal to omega squared times A. Usually written in the other direction. They usually write A first. So that means the maximum acceleration theoretically should be equal to the amplitude. This A, remember, is the position amplitude, the maximum position stretched from equilibrium times omega squared, which is K over M. But this is usually how it's referenced right here. So coming back to here, where was I? Did I lose? Back to here. We can now write, we can insert that in for A max, right? So we have A of t is A max cosine omega t. But I'm just going to stick that in for A max. So we end up with A omega squared cosine omega t. Now there's one other thing we have to just check to make sure that the directions all work, right? So let's think of this. When we're all the way stretched out over here in the beginning, about to release it, in a couple moments later, when it's now moving leftward, the acceleration is left. Left is negative, right? Left is negative. If we're just using the regular cosine function, it doesn't give us negative values right away. It gives us plus values, right? We need it to give us negative values right away for the reason I just stated. It's moving, as it moves leftward right from the beginning, it's accelerating in the leftward direction because the net force is leftward, negative, the spring force. So what do I have to do to fix this? Just multiply it by negative. Boom. Right? Now, after it's released, at release, it has a maximum acceleration. And these are all negative accelerations as it moves to the left, which we know it has to have, right? As it moves to the left, these are negative accelerations because it's accelerating in the leftward direction. So that means the last thing we had to do to fix this was multiply all this by a negative. And there you have it. That is the final model for the acceleration versus time. And it's also worth pointing out that when, if I could draw one other thing here, if we looked at a velocity versus time graph, and we saw that it looked like just say it looked like this. Actually, it's not really right. Sorry. For the one we've been doing, it starts out moving to the left, right? If we looked at the acceleration versus time graph for that same motion, again, remember that when the velocity is 0, that's at one of the endpoints, right? That's at one of the endpoints. So when the velocity is 0, which is all the way at the endpoint, which is here, the acceleration has to be a maximum at this position. So when the velocity is 0, which I'm showing here. Something doesn't seem right about this. Sorry. Think about this. Oh, I'm making a mistake. So sorry. So sorry. Velocity starts out at 0, right, and then becomes negative. So I just drew it wrong. Like this. So when in the beginning, when you release it, and the velocity is going to be momentarily, just moments after that, to the left, negative, then the acceleration would have to be a maximum. Right? So that would correspond to this point here. And then when the velocity is negative and maximum, which is when it's in the middle, right here, maximum speed heading to the left, that's when there's no force in the spring and therefore no acceleration. So this is right here, again, a maximum negative speed, like I was just saying, passing through equilibrium. That would have to correspond to 0 acceleration. And then the next one, when the velocity is 0, is now when it's on the other side, stopping, right here. This would have to be a positive because now the spring force is pushing to the right, right? Well, even before that, it was pushing to the right. Even as it goes in, it's still pushing to the right, still pushing to the right. But at that position, now we would have to have a maximum. Again, no velocity, that's this one right here, no velocity, but a maximum acceleration that's going to be in the positive direction, right? So that would have to be sorry, am I saying this backwards again? Velocity of 0. Oh, I was in the wrong one. Sorry. Well, I was referencing the speed in the middle. So I was referencing right here. When it has maximum speed, it would have 0 acceleration. Oh, I did that. Okay. Maximum speed, yep, 0 acceleration. Then when it has 0 speed on the other side, the acceleration would end up being to the right. So my point is you'd end up with these, it's hard for me, to be honest, I struggle with drawing these. You'd end up having the same features, and it's hard for me to line them all up. And in fact, the x-axis wouldn't be there. The x-axis would actually be right in the middle like that. Sorry that I still have a hard time. But my point is there's still these correlations between when the speed is moving along really fast, or when the speed is 0, for example, it would have a maximum acceleration. That's at the endpoints. That's what I was trying to bring up those graphs. Maybe I'll find one and I'll post a few. But all three of those graphs, again, model each of these individual quantities. So the last thing I'll do is write them all down. X of t is a times cos omega t. V of t is equal to a times omega sine omega t with a negative, and then a of t is negative a omega squared cosine omega t. Yeah, and in all cases, omega can be expressed as square root of k over m. And my last, looking down, not realize you couldn't see that. And my last point is to point out that omega is also equal to 2 pi f. Because remember, omega is 2 pi over t, right? And we already knew that t is 1 over f, and f is 1 over t, right? So if I take my t here, think of this as 1 over t, I can technically remove 1 over t and just put f in its place. I'd end up with 2 pi f. So the last point is that omega can also be expressed as 2 pi f, where f is the frequency in hertz. So if it's going back and forth, boom, 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 5 times, full cycles, 5 full cycles in 1 second, we'd say that's a frequency of 5 hertz. So in for omega in these places, you can either put k over m, square root, or there's other problems in the AP exam that reference this one, 2 pi f. All right, I've finally gotten through what I wanted to do today. I am going to end up with 1/3 lesson and the sequence of lessons. The third one is going to be just some problems. I'm going to do a couple, because that's all the theory. I've pretty much taught you all the concepts and all the theory behind all of it. Maybe a little bit about damping and frictional forces, because they do mention some questions do mention that. But more so in the third, again, lesson is going to be some computational problem solving using all this stuff. All right, that'll do it for today. See you guys later.